Hi guys, so today I'm gonna do an exam run review. We're gonna cover some content from chapter 1 to chapter 3. All of these questions I gather are gonna be from the book right here. So if you want any more practice problems, you can always go to the book and you can just look over the skill builders and you're gonna be able to get a lot more practice before the exam. I thought just doing an online review, it would be pretty nice, just because I know a lot of people, they may not be able to go to the review on a Monday after class. So I thought it would be much nicer to do it online. So then maybe on Tuesday you can come over to my office hours and I will be able to answer any more questions if you may have. So then let's see, we can get started. So how many hydrogens are in this carbon? Determine the number of hydrogen atoms connected to each carbon atom. So let's see. So I guess we already know that a normal carbon without any formal charges is gonna be able to do a total of 4 bonds. So then carbon can do 4 bonds. So then, for example, let's look at this carbon. We can see 1 bond, right? So then we can assume that there's going to be other 3 bonds that are hydrogen atoms. Or for example, let's look at this carbon. This carbon, do you think it's going to have any hydrogen atoms or not? So if we count, we have 1, 2, 3, 4. So technically, we cannot have any hydrogen atoms in there because we will be breaking the octet rule. So that one doesn't have any hydrogen atoms. And we can look at the other problem. Let's look at this carbon down here. This one has 1, 2, 3, 4 bonds. So it's just gonna be there and it's just not gonna have any hydrogen atoms. Well, this one in here, we have 1 bond, right? And we need 4, right? So this one's gonna have other 3 hydrogen atoms. And then if we look at this one down here, we have 1, 2, 3. So I think we can assume there's going to be another hydrogen atom. And then in this one down here, we have 1, 2, 3, right? So then we need another one. And we have 4 bonds down here. And same goes in here. We have 1 bond, so we need 3 more. So when you're approaching this type of problems, I would say I normally try to count down my number of bonds that my carbon has already. And then if I have 4, then there's not going to be any hydrogen atoms. But for example, if I only have 2, then I can assume I'm going to have another 2 or 3 or 4, 2 or 3 hydrogen atoms. Let's see, now we can draw some bond line structures. So draw a bond line structure for each of the following compounds. We have CH3, CH2, 3, COH. Okay, perfect. So bond line structures are normally these ones down here, the line angle one. So then what I normally do is I draw them in Lewis and then afterwards I just translate it. But I would recommend to do that just because it's gonna let you know that you're correct. But if it's much easier for you to just do it bond line, then you can do that. But I normally do Lewis structure first and then I translate it to a bond line. So then let's see, we have CH3, CH2. So then we need to know that carbon has 4 bonds. Oxygen can normally do 2 bonds and hydrogen can do only 1 bond. So then our carbon right there, we're gonna focus on this carbon. That one we can do 4 bonds, right? So then we have an OH in here. So then this one we have 1 bond for this O, so then we need another bond for that one, so we can put our H down there so we can only have 1 bond. And then we have our CH3, CH2, CH3. So then if you ever encounter that means that there's gonna be, like, since it's in a group, it means that you have like this match, like CH2, CH3, CH2. It's the same thing, just multiplied by 3. And what it's assuming for you like when it's on a parenthesis, it means normally that it's gonna be on that same carbon. So then, for example, if I was to complete my structure, in here have CH2, CH2, CH3, CH. So then I have one group down here, right? So then in here I will have another group. And then in here I will have another group as well. Okay, so since we already know how low structure is gonna look like, then we're gonna try to translate it to a bond line angle structure. So then the next step is that, in bond line structures, we normally don't see like the hydrogen atoms. We just assume that they're there. So normally what I do is that I just draw the same structure and I just erase the hydrogen atoms. Except, as we know, in bond line structures, they do show the OH groups, or anything that's not a carbon or hydrogen, they do show them. So we're gonna keep that OH group in there. And then next, we're just gonna change their structures so they're not like linear. Instead, they're at an angle instead. So you have C, 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 and then we have this O. And then we can translate it afterwards to a bond line structure. So then we have this, 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 and then this, and then this. So that one will be like your bond line structure for that one. And then let's see, let me erase this one down here for a second. Okay, so we're gonna do the next problem instead. Okay, so we can get started with the beginning here. We have CH2, right? So we have CH, H, and then we have a double bond, right? This carbon has already its 4 bonds, so we're good to go for this one. Then we have C, H, and then an O. So then let's see, CHO. Okay, perfect. So then we have C, we have an H, and this one can only do another 1 bond, right? So this one is good, and then we're gonna join this oxygen. And then oxygen can do 2 bonds, right? So then we're gonna add this one. Our oxygen is good. And then we have hydrogen, hydrogen. This carbon is good because it has its 4 bonds, CH. And remember that what we said, when it's like on a parenthesis, we're just assuming that there's gonna be this CH3 times 2. So it's gonna be represented in this way. And it's gonna be located on that same carbon as we said. So then we have CH3, or let's see, let me erase that. We have C, H, 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 and then we have another CH3 in there. And then if you want, you can add your lone pairs. You don't really need to add them, but I normally do. Then we're gonna do the same process. We're just gonna remove the H's. So then C, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, oxygen, 1, 2, 3, yeah. And then we're just gonna, instead of linear, we're just gonna put them at an angle as we said. So then let's see, we have C, O, C, this one in here. Okay, perfect. So then now we can just do this. 1, 2, 3, O, and then 1, 2, 3, and then this. So that will be our bond line structure for that one down there. For these structures, I would say that you of course need to practice a lot, but as long as you know your bonds, like for example, as long as you know that carbon has 4 bonds, oxygen has 2 bonds, and hydrogen has 1 bond, and nitrogen can do a total of 3 bonds, I think you can already assume where they're going to be located. And then the next one, which pair of the following compounds are constitutional isomers? So constitutional isomers are normally like, for example, we have like the same structure, they have the same like molecular formula, let's say like C3H8 for example, but they're just gonna be represented different. So then if we do this, I would say I would do another one. I would probably choose C5H12, and then we have 1, 2, 3, 4, 5. So this is one way of representing this molecular formula. But then there's different ways of representing molecular formulas. So for example, this one can be 1, 2, 3, 4, and instead this one can go like this, and it still represents the same molecular formula. It's just an isomer of it. So that's mainly what constitutional isomers they are. They have the same molecular formula, but they have different arrangement. So what I normally do for this type of problems is that I normally count the number of carbons it has, and then most of the time that's going to tell you whether they have the same molecular formula or not. So then let's see, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has C9, 1, 2, 3, 4, 5, 6, 7, 8. So this one has 8 only, and then 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can say that A and D, they're gonna be eliminated because they only have, A has 9 carbons and D has 10 carbons. And B and C, they have the same number of carbons. So B and C, they're gonna be constitutional isomers because they're arranged differently, but they have the same molecular formula. And how do I know that they have the same number of hydrogens? So then when you count hydrogens, for example, and there's not like, for example, if in a molecular formula there's a double bond, then let's say there was a double bond in here, then they wouldn't have the same amount of hydrogens, but instead this one doesn't have any double bonds in there. So we can use this formula down here. So when there's no double bonds, we can do this formula. So we have 8 carbons, we multiply it by 2, we have 16, and then we add it by 2. Then there's gonna be 18 hydrogens. The same goes for this one. We have 8 carbons, we multiply by 2, we have 16, and plus 2, we have 18. So this formula doesn't work when there's a double bond, but since there's no double bonds, we can use it. So hybridization. So a lot of people, they have a hard time doing hybridization. So then when you're doing hybridization, I do it in this way. So then sp3, normally I do it when there's 4 orbitals, or when I'm able to do 4 circles. sp2, I normally look at it when I can do only 3 circles. And sp, I normally look at it when I can do only 2 circles. So then I can think about it in this way. So we have sp, right? So I have 1 and 1. So then I just add them up and I have 2. So this 2 is just going to represent 2 circles. And then here we have 1. 1 plus 2 is 3. Then we represent 3 circles. And then it has S1 and P3. We have 1 plus 3. we have 4 circles. And for example, a circle, it can be 1 bond. A circle can be also 2 bonds. A circle can be 3 bonds. And then a circle can be a lone pair. So I want you to think about it like that. Because you see, for example, that this one in here, I don't count it as 2 circles. I just count it as 1. So I just count it as a group. For example, we can try these problems in here. So then determine the hybridization state of each carbon atom. So for example, in here we only have 1, 2, 3, 4. So when we can do 4 circles, we said that it was going to be sp3, right? I can do a little note for you guys. Sp is going to be 2 circles. sp2 is going to be 3 circles. And sp3 is going to be 4 circles. So then let's look at the next carbon. We have, oh no, let me erase that. Okay, perfect. And then we have 1, 2, and 3. So then we can think that this one is gonna be sp2. And they have 1, 2, and 3. This is gonna be sp2. And they have 1, 2, and 3. So that one's gonna be sp2 as well. Let's look at B. We have 1, 2, 3, 4. We have sp3. We can do 1, 2. This one's gonna be sp. 1, 2. This is gonna be sp. 1, 2, 3, 4. This one's gonna be sp3. 1, 2, 3, 4. This is gonna be sp3. And then let's see C. We have 1, 2, 3, 4. This one's gonna be sp3. 1, 2, 3. sp2. 1, 2, 3. sp2. You have 1, 2, 3, 4. sp3. And then let's see on letter D, we have 1, 2, 3. We have sp2. We have 1, 2. This is gonna be sp. 1, 2. This is gonna be sp. 1, 2, 3. This is gonna be sp2. And then let's look at letter E. We have 1, 2, 3. This is gonna be sp2. They have 1, 2 sp. So you can already assume that we have a pattern down there, right? And I'm not sure if you're really gonna get like a carbon with like that has like lone pairs, but I would tell you when it has lone pairs, you count it as if it was like a bond. So then a lone pair is gonna create 1 circle. So then we have 1, 2, 3. So it's gonna be sp3. Just in case if you get a problem with lone pairs. Then B, SFPR theory. So then you have to know the names of the structures. So we have tetrahedral, trigonal pyramidal, bend geometry, trigonal planar, and linear geometry. So tetrahedral, for example, is going to be shown like this. It's normally going to be an atom that is sp3 hybridized. So we have 1, 2, 3. 1, 2, 3, 4. And it's going to be sp3. As you can see, this carbon doesn't have any lone pairs, so it makes it a tetrahedral. And trigonal pyramidal, sp3, 1 lone pair. So trigonal pyramidal can be represented in this way. We have 1, 2, 3. And why is it sp3? It's sp3 because of the same logic that we learned before. So we have 1, 2, 3, 4. So it's going to be sp3. But it has 1 lone pair. That's what makes it trigonal pyramidal. Then we have bend geometry. It's normally represented like this. And as you can see, it has 2 lone pairs. And trigonal planar. This one can be represented, I think, in this one down here. Trigonal planar is normally sp2. So you have 1, 2, 3. And as you can see, the difference with trigonal planar, trigonal pyramidal is that trigonal planar is not gonna have any lone pairs, while trigonal pyramidal does have lone pairs. And then linear geometry, SP, no lone pairs, and that can be represented in this way. We said that it's gonna be an SP, so we have 1, 2, SP, and no lone pairs. So we're gonna practice a little bit on how to predict that geometry for each molecule. So then let's see. Let's look at A. So then we have 1, 2, 3, 4 is sp3, and it doesn't have any lone pairs. And if we go back, sp3, no lone pairs, we have a tetrahedral down there. And now this one we have 1, 2, 3. It's gonna be sp2. sp2 and no lone pairs. sp2, no lone pairs. We have trigonal planar. And then we have 1, 2, 3, 4. sp3, no lone pairs. We have a tetrahedral. And then we have in here 1, 2, 3, 4. sp3, no lone pairs, tetrahedral. And I think this is I really like this example. That one down there, you can say it's a pretty good example because it's gonna let you know the difference between trigonal planar and trigonal pyramidal, and I really like that one. So for example, as you can see here, we have 1, 2, 3. This is gonna be sp2. We have 1, 2, 3, 4, and this is gonna be sp3 lone pairs. So then let's look back. It only has one lone pair also. sp3 and one lone pair. This one's gonna be trigonal pyramidal. But as you can see, this one's sp2, no lone pairs. sp2, no lone pairs is gonna be trigonal planar. And I thought that, for example, for test, normally it's much harder than what I showed you guys. So I think it would be nice to see like a whole molecule and actually like determining like the geometry for it. So then let's see. I think we're focusing on this carbon. Then this carbon down here, then in this oxygen, then for this one we're focusing on this carbon down here. These are two different carbons, we're focusing on this one, and then we're going to be focusing on this nitrogen. Okay, so then we're going to be looking at this one first. Okay, so let's determine if it's sp, sp2, or sp3. So we have 1, 2, 3. It's gonna be sp2, no lone pairs. So I would say we can say that one's trigonal planar. Let's look at the second one, this one right here. So then we have 1, 2. But let's look at this. We have 1, 2 bonds, right? And this carbon doesn't have any formal charges, so we have other 2 hydrogens in there, but they're just not shown. So we have 1, 2, 3, 4. That one's gonna be an sp3, and no lone pairs, so it's gonna be a tetrahedral. Okay, perfect. And then we can look at that oxygen down there. So then this one, we have 1, 2, 3, 4. We have sp3, but this one has 2 lone pairs. And we saw that normally when it has 2 lone pairs, it's gonna show bent geometry. Then let's look at the third carbon and the next molecule. So then we have to count first how many hydrogens we have. So this one only has 1 bond for now. Then we can, 1 bond, but we need 4 bonds, right? So this carbon is gonna have 3 hydrogens. And now we can determine if it's sp, sp2, or sp3. So we can look at this. We have 1, 2, 3, 4. So it's sp3, no lone pairs. It's gonna be a tetrahedral. But we look at this carbon down here. This carbon has 1, 2, 3, and 4 bonds. So no need to put any hydrogen atoms in there. Have 1 circle, and then we have 2 circles. So this one's gonna be an sp. sp, no lone pairs. I would say that one's linear. Oops. And then we have to look at the nitrogen. So we have 1, 2, and 3. We have 3, so that's gonna be 1, 2, 3. Oops, I forgot that lone pair. So we have 4 circles. That's gonna be sp3. We have 1 lone pair. So I would say this one's definitely trigonal pyramidal. If you still need more practice, you can always look at the book, and these ones are some examples from the book, but then I think there's like 6 or 7 more, and of course in the book they have the answers for it, so I think it will be a pretty nice practice for you before the exam. And okay, increases boiling point. So there's different factors that increase boiling point. I really want you guys to understand how boiling point works, just because I think you may have 1 or 2 problems dealing with boiling points, so I want you guys to be able to determine which one has a higher boiling point than the other one. So then boiling point is normally affected by 3 different factors. The fluorine dipole-dipole interactions, or basically how I think about it is, the more carbon atoms you have, the higher the boiling point. So for example, if you look at the comparisons, this one has only 4 carbons and it has a boiling point of 0 degrees, but this one has 5 carbons and it has a boiling point of 36, but this one has 6 carbons and it has a boiling point of 69. So you can see every time you add a carbon atom to the molecule, you're gonna have a higher boiling point. Another thing that is gonna affect your boiling point is gonna be hydrogen bonding. So hydrogen bonding can be represented like this. It's when you have an OH group or an NH group. So, but they have to be together, just like here, just like how it's shown in there. So for example, this molecule doesn't show hydrogen bonding because that oxygen doesn't have any hydrogens with it. But if you compare the boiling points between the two of them, the one that has an OH group or a hydrogen bond has a higher boiling point than the other molecule. Another thing when you consider hydrogen bonding is, for example, if we look at this NH in here, it only has 1 hydrogen bonding right there, but this one has 2. So every time it has like more hydrogen bonding, the boiling point is going to increase. So you can see here we have no hydrogen bonding. It has a boiling point of 3.5. It has 1 hydrogen bonding. It has a boiling point of 37. It has 2. It has a boiling point of 49. Then the last thing that is going to increase your boiling point is going to be dipole-dipole interactions. So dipole-dipole, I think about it like electronegativity in some way. So then, for example, we know that oxygen is going to be more electronegative than a carbon. So the oxygen is going to carry the negative charge, and the carbon is going to carry the positive charge. So that's mainly what is dipole-dipole interactions, when they have like electronegative activity. That's why this one in here doesn't have any dipole-dipole interactions, because it's interacting just with different carbon atoms. And you can see in the numbers below, you can see how melting point and boiling point are affected by dipole-dipole interactions. You can see this molecule that doesn't have any dipole interactions, it has a boiling point of negative 6.9, but the one that has dipole-dipole interactions, it has a boiling point of 56.3. And well, good thing to know, the only thing that decreases the boiling point is gonna be branching. So branching is normally when, for example, in here we have no branching. In here we have kind of like in between branching, but not really, and this is fully branching. So it's just when your molecule is just like this instead of being just linear like this. And that does have an impact on your boiling point. You can see how it's decreasing from no branching to mid branching to being fully branched. And now we're gonna compare boiling points. So then let's see. We know number of carbons are gonna increase. Number of carbons, then hydrogen bonding, right? Maybe dipole interaction as well. Then what's gonna decrease is gonna be branching. So we have to think about those factors. Let's look at A. Okay, so let's make it easy. Let's count how many carbon atoms we have. We have 1, 2, 3, 1, 2, 3. We have 6. 1, 2, 3, 1, 2, 3. We have 6. Let's see. We have no hydrogen bonding. No hydrogen bonding on this one. Okay, so we can eliminate number of carbons, hydrogen bonding. I would say there's some dipole interactions, but the two of them, they have the same amount of dipole interactions, I would say. So I would say that they will have the same dipole interactions, so this one's just gonna be eliminated. So how else can we compare it? Well, we're forgetting about branching, so the branching decreases it, right? So then this molecule down here has some branching, right? So it's gonna have a lower boiling point than this one. So this one is gonna have the higher boiling point. Okay, perfect. So we can go to B. Let's count the number of carbons. We have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5, 6. And we don't have any hydrogen bonding. We don't have any dipole because we don't have any other atoms than carbon and hydrogen. And they both represent branching. So the main difference is gonna be the number of carbon atoms. And we know as you have more carbon atoms in your molecule, the more is gonna be your boiling point. So this one's gonna be the higher boiling point. And let's see, we can look at the next one. We have 1, 2, 3, 4. We have 4 carbons. We have 1, 2, 3, 4. We have 4 carbons. And then, for example, Let's see. We have the number of carbons. We have to look at hydrogen bonding. Then we have this one down here. So then there is hydrogen bonding for this one. And comparing to the other molecule, no hydrogen bonding. They do have some dipole interactions. This one has some dipole, but for example, this one's gonna have some dipole as well if you kind of think about it. So then, let's see, we have hydrogen bonding, dipole. There's no branching. So then, since this one has hydrogen bonding, this one's gonna be the higher boiling point. And then we can look at letter D. So then, let's see, we have 1, 2, 3, 4. We have 1, 2, 3, 4. We have hydrogen bonding, hydrogen bonding. They both will have the same dipole because it's OH. So then, what's the main difference? Branching. So then this one's branching, it decreases boiling point. So this one's gonna be the higher boiling point. So hopefully that was helpful. Possibly for when you're comparing boiling points, I would say for you just to remember that what the factors that increases and decreases boiling point. Just remember that you increase your boiling point by the number of carbons you have, by doing hydrogen bonding, by doing dipole-dipole interactions. While what decreases your boiling point is gonna be branching. So now we can do some resonance structures. So I saw that a lot of people were having a lot of problems when doing resonance structures, and at the beginning it can be very hard, to be honest. So I just wanted to give you guys some tips about it, but I would say the best thing you can do is just doing practice. I know they do take a lot of time, but afterwards they're gonna be really easy and they're really fun to do. So let's say curved arrows. These factors, for now, we're just doing resonance, so these ones are just gonna be for resonance. So then a tail, it can be placed on a double bond, triple bond, or lone pair. And why not place it on a single bond? Because if we place our tail on a single bond, we will be breaking a single bond, which violates one of the 2 rules for resonance, which is to not break single bonds. And then the head, it can be placed on an atom or on a bond. The next thing for you guys to know, I feel like you need to know the formal charges for oxygen, nitrogen, and carbon. So I wanted to take some time for you guys to know the formal charges for each atom. So then let's see. So when oxygen has 3 lone pairs, it's only gonna be able to do 1 bond. When oxygen has no charge, and when it's on its regular state, it can do 2 bonds and it's gonna have 2 lone pairs. But when oxygen has a positive charge, it's gonna have 1 lone pair and it's gonna have 3. It's gonna do 3 bonds. Then let's look at nitrogen. Nitrogen with a negative charge is gonna be able to do 2 bonds and it's gonna have 2 lone pairs. When nitrogen it's on its regular state, it can do 3 bonds and it's gonna have 1 lone pair. And then when nitrogen has a positive charge, it has no lone pairs, but it's gonna have 4 bonds. And then carbon with formal charges. So we know Carbon, when it's in its regular state, is just gonna be able to do 4 bonds. Carbon with a positive charge, it only does 3 bonds. So for example, we have 1, 2. So just 3 bonds, 1, 2, 3, and no lone pairs. So then when it's positive, no lone pairs for carbon. But when it's negative, it can do 3 bonds, but it's gonna be a negative. And of course, a lone pair. Once we know all of that, I would say we can begin just by looking at whether we're breaking rules or not. So let's see. Breaking rules, determine whether the curved arrow violates either of the 2 rules. So we have 2 rules when doing resonance. We have the octet rule or breaking a single bond. So let's look at this one. Are we breaking any rules? Octet rule, or we're breaking a single bond, or we're not breaking any rules? Well, we first said that the tail, it cannot be placed on a single bond, right? So we're breaking a single bond. Let's look at the next one. Let's see. So nitrogen has a positive charge. It already has 1, 2, 3, 4 bonds. So if we follow this arrow that it's breaking this double bond and then it wants to place it wants to make another bond on that nitrogen, it's gonna give a nitrogen a 5th bond, which wouldn't be good because we'll be breaking the octet rule. So octet rule is broken. Remember, nitrogen with a positive, it can only do 4 bonds. So then, if we add another bond, it will be doing 5 bonds, and we don't want that because nitrogen with a positive charge can only do 4 bonds. And then that's it. We can do the resonance for this one. We have 1, 2, 3. 1, 2, 2, 1, 2. So then we can see here that it is able to do it because we can, as we said, we can think about it this way. We have a triple bond. We're breaking it to put another lone pair on that atom. Then that's it. Then that carbon is gonna hold a positive charge and the nitrogen is gonna have a negative charge. We're not really breaking any single bonds, and it is possible, considering the octet rule, it is possible for the carbon to hold a positive charge, and it is possible for the nitrogen to hold a negative charge. It can do 2 bonds, and it can have 2 lone pairs, so this one's pretty good for now. And then let's see, we can look at this one down here. So then we have 1, 2. So then nothing is affecting our oxygen in here. So our oxygen is in its regular state. Oxygen in its regular state, it can only do 2 bonds and it has 2 lone pairs. So it's just gonna stay like that. So then if we're breaking that double bond and we're adding another bond to that oxygen, that will be breaking the octet rule. So this arrow will be breaking the octet rule. Like the tail, it is good. It is placed on a double bond. But the thing is that if we add another bond to that regular state oxygen, it's just gonna be breaking the octet rule. Okay, so we're gonna practice practicing formal charges of resonance. So we're gonna draw the resonance structures that is indicated by the curved arrows, and we're gonna include the formal charges. So then let's get started. We can draw the resonance structure for this one. Let's see. It's not gonna look pretty good since I'm drawing on my iPad, but I will try my best. Let's see. Oxygen. We have 1, 2, 3, 4, 5, 6, negative. Okay, so then this one's not really getting affected by it. This arrow is moving it to here. Then this arrow is moving it to here. We're making a double bond in there. This one's gonna become negative. Let's see, this one's good. This one stays positive because we know nitrogen with 1, 2, 3, 4 bonds is gonna be a positive charge. So then we have this one down here, this one down here, this one's good. And let's not forget about this carbon down here. So then remember, a carbon with no lone pairs is gonna be positive. So then this carbon, it originally only had one hydrogen bond, and this one still stays only one hydrogen bond, but it doesn't have 4 bonds, right? And it doesn't have any lone pairs. So then this carbon is gonna hold a positive charge. Okay, perfect. So then we can look at the next one. Have 1, 2, 3, 4. We have our oxygen. So then let's see. We're breaking that double bond and putting those electrons on that oxygen. So we have 1, 2, 3, 4, 5, 6. Oxygen, 1 bond. It has 3 lone pairs. It's gonna be negative. So then we're moving this double bond to this side down here. So then we're moving it in here. So then our carbon is stable in here. It has its 4 bonds. But then let's remember, this one has 1, 2, 3, 4. This one has 1, 2, 3. 3 bonds, carbon, 3 bonds, no lone pairs. It's gonna hold a positive charge. So for this type of problems, and since you're not really used to visualizing how many hydrogen atoms is gonna have your carbons, personally, when I did a test, I would actually draw the hydrogens. For example, in here we have 1, 2, 3, 4. Then this one will be the same. This one has 1, 2, 3. This one has 1, 2, 3, 4, 1, only 1 hydrogen. The nice thing about drawing your hydrogens is that you're gonna be sure that you're not breaking any octet rules. The thing is that I always say about resonance is that we're just moving electrons. So then your molecule is gonna be the same as the last one. The thing is that the electrons, they're just gonna be displayed differently, but they're still representing the same molecule. That's why we're not breaking any single bonds, because if you were to break a single bond, then it wouldn't be the same structure, right? So then let's see. Resonance structures. Draw the resonance structure for each of the following compounds. So when I do resonance structures, what I do is that I try to first draw my lone pairs. So oxygen with 2 bonds is gonna have 2 lone pairs. Okay, so how would I approach this problem? Well, normally when I'm just beginning doing resonance, I would just draw how many hydrogens I have. So this carbon has 3 hydrogens, this one has 3, this one has 1, 2, 3. So technically, I would say we can't really touch any of those carbons just because octet rule, they're pretty good for now because they have their 4 bonds. They don't have any lone pairs. So we cannot really do any resonance structures with those. But our oxygen has lone pairs. and our carbon in there has a positive charge. So actually these two, they can interact with each other. So then if we have this one in here, this one in here, then we have this in here and here. So then we can all remember our tail of our arrow is gonna either be placed on a lone pair, on a double bond, or a triple bond. So in here we have lone pairs, and we're gonna place that on this one in here, on this bond in here, which is gonna create a double bond, and it's gonna fill the octet for that carbon in there that had a positive charge. So then we still have our carbons hydrogen bonds. We have carbon hydrogen. The only difference is that this carbon is gonna have its 4 bonds. It's gonna have a filled octet, and this oxygen is gonna have 3 bonds. So then let's see an oxygen with 3 bonds and 1 lone pair is gonna have a negative or positive charge. Well, it's gonna have a positive charge because we know that oxygen with a negative it's gonna have 3 lone pairs. Okay, so we can do the next one. Let's see, our nitrogen, it has only 1 lone pair. Oxygen has 2 lone pairs. Okay, so let's look at our carbons. First of all, 1, 2, 3. We have 1, 2, 3. We have 1, 2, 3. And this carbon is pretty good because it has 4 bonds already, the next one. So then again, these ones are pretty good. Our main focus is gonna be this section down here. So then what can we do? So what I would recommend for this problem is that so we have lone pairs and then we have a double bond. So what I would do is that I would break this double bond and then put it on that oxygen, and then if we do that, our carbon is gonna have a positive charge, right? Because remember, carbon with only 3 bonds, no lone pair, is gonna be positive. So when a carbon has a positive charge, that means it can always accept electrons. So you can always do another bond with it and just stabilize it and just make so your carbon is gonna have 4 bonds and it's gonna be at a regular state. So then I would use this lone pair down here in that nitrogen and then place it on that bond in there to create a double bond with our carbon. So then that carbon is at a regular state. So then let's see, we have nitrogen in here, here, here. Remember, we broke that bond with that oxygen, so our oxygen is gonna have 3 lone pairs. Remember, 3 lone pairs, negative charge for oxygen. Then we decided to put a double bond in there. So our carbon has already its 4 bonds. And then our nitrogen doesn't have any lone pairs, right? Because we used that lone pair on that nitrogen to make that double bond for that carbon. So then nitrogen, 4 bonds, no lone pairs, is gonna have a positive charge. Let's see. No, sorry. sorry about that. So then let's see. Have CNOF, a nitrogen with a positive. Yeah, it's gonna have a positive charge. So that would be a resonance structure for that one. And I don't really think we can do another resonance structures afterwards. And then we need to know which one's a major and a minor contributor. So identifying major and minor contributors. More significant if it has a great number of octets, which particularly means a number of bonds. If it has fewer formal charges, so the less formal charges, the better. Formal charges are the positive or negative charge, like the positive or negative charge placed on an atom. Then if we have a negative charge, we prefer it to be on the most electronegative. And then we have a positive charge, we like it to be on the less electronegative. Also, we need to consider that resonance forms can create equally good Lewis structures. What it technically means is that, for example, if we do resonance on a structure like this one, if you look at all of these ones, they look the same, right? They have the same formal charges. They have like 2 oxygens with negative charges. They have a 1 double bondage. So then technically, if you look at them, they look different. No, they look the same technically. The electrons are just represented in a different way, but technically they will have the same equivalency. So then we're gonna draw all the significant resonance forms, and then we're gonna rank them from most significant to least significant. So we're gonna draw the resonance for this one. So then remember tail can be on a double bond or electron pair. So I'm gonna move this one up here. So you have 1, 2, 3, 4. You have an oxygen negative. Then we can always move this one in here. So then our carbon has 4 bonds. Okay, perfect. So then we have 1 resonance structure. And then we can always move this double bond in here. And they have 1, 2, 3, 4. We have oxygen, 1, 2, 3, 4. And then this is gonna be a positive charge. We have a positive in here, we have a positive on that one. And then I would say we can always move this one back. And then we can move this one, let's see. Have 1, 2, 3, 4, 5. Oxygen, 1, 2, 3, 4, 1, 2, negative. And then we have this one in here. So this one's gonna have a positive, so then we can always move this one in here. And then our double bond is gonna be moved to this side. And then our carbons, instead only have 1, 2, 3, it doesn't have any hydrogens. So in here, it won't also have any hydrogens. Like in this one, you can see here we have 4 bonds. We have 3 bonds, no lone pairs. It has a positive charge. So then if we look at all these structures, for example, we have an oxygen on negative, right? We have the same amount of bonds. We have 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This one has 8. Have 1, 2, 3, 4, 5, 6, 7, 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. So they all have the same number of. They have the same number of bonds. They have then an oxygen with a negative. They have the positive on a carbon. So, and we know that resonance forms can create an equally good Lewis structure. So that means that there's no major and minor contributors. They all the same contributor. And then all of these ones, they're all resonance forms. So then this one is gonna be the major, just because it doesn't have any formal charges, right? It doesn't have any positive, any negatives. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 bonds. It doesn't have any formal charges. So then that's what makes it a major. Well, these ones are the minor, because we have formal charges and we have the least number of bonds. And then we can look at this one down here. So then we have CH3, carbon, hydrogen, carbon. We have 1, 2, 3, nitrogen. And we know carbon with a negative is going to have 1 lone pair. So then we can always do resonance structure for that one. See, 1, 2, 3. This one doesn't have any. So then technically, this nitrogen atom, this lone pair is kind of stuck, just because it can't really interact with this carbon for now, just because carbon is at a regular state. So it can only do 4 bonds for now. So then the only thing that we can interact is with that triple bond down there. So then what I'm gonna do is that I'm gonna break that triple bond to a double bond and place one of the bonds to that nitrogen. Let's see. So then nitrogen with 2 bonds. So it's gonna be a negative charge for that one. Our carbon, it only has 3 bonds. It has no lone pairs, so it's gonna be a positive. And then let's see. And then our carbon has a negative. So technically, what we can do now is that we can always move this lone pair, and then we can make a double bond in there. So we can do CH3, CH. You have double bond C. This one's fuel octet. Okay, perfect. So then we can look at all of them right now. So then we have to compare all of this one: CH3, CH, C, and negative, 2 lone pairs, 1 lone pair, 1 lone pair. Okay. So we have to see from these ones, we have 1, 2, and 3. We have to compare which one, which one's a major contributor and which one's a minor contributor. So let's see, let's look at back our rules. We need it's negative charge on most electronegative. We have a positive charge on the least. We want to have most number of bonds. And let's see, am I forgetting of anything else? First number of octets, and we want the fewest formal charges. Okay, so I would begin by counting the number of bonds. So I have 1. I can also count the hydrogen bonds in there. So we do, let's see, let me restart for a second. Let me add the carbon with the hydrogens. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this one has 9 bonds. And this one has 8 bonds. So I would say that this one will be the major contributor. And then now we can compare these two. So that this one has more formal charges, so it's not really looking good for that one. This one has less formal charges, so it is pretty nice. And so then we already saw number of bonds, which one has more and less formal charges. We don't have any positive charges, so we don't really have to look at that. But we do have a negative charge. I mean, this one does have a positive charge, and it's on a carbon, which is nice. But then we have to look at this. We have a carbon with a negative, right? And carbon with a negative is not really the most electronegative. While this one has a nitrogen with a negative. And looking at our molecule, it is the most electronegative. So then this one is going to be the major, the first place. This is going to be second major. And this is going to be the minor. So then when comparing these two down here, the thing what I would say that really let me know that this one was going to be more major than the other one was that this one had the less formal charges, and also the two of them, they had the same amount of bonds. The difference was that, look, the second structure has a total of 3 formal charges, while the third one, it has only 1 formal charge. And we really want to have the least number of formal charges. So that's what really pointed me out that the third structure was going to be more major than the second structure. So this one's going to be major, this is going to be second major, and this is going to be the minor. Okay, so now we're getting to the hard part. We're going to do Bronsted-Lowry base, Bronsted-Lowry acid, Lewis acid, and Lewis base. So I know that a lot of people got confused about the definition about bases and acids. What is a Lewis acid? What's a Lewis base? And to be honest, it can be pretty confusing. But they do correlate with each other. So, for example, when I was doing a test, what I would do is just memorize the definition of one thing. Like, what is a Bronsted-Lowry base? So then I would just use that to guide myself. So, for example, I would create a chart like this when I'm doing a test. So, for example, I would label base, acid. Okay, perfect. We have base, acid. And then I would put Bronsted in one. And then I would put Lewis. Okay. So then a base is going to be a Bronsted base. It's going to be a proton acceptor. So then if our base is a proton acceptor for Bronsted, then that means that the acid is a proton donor. So then Bronsted is talking about protons, while Lewis is talking about electron pairs. So then if our base, for example, for Bronsted is a proton acceptor, that means, let's see, electron pair, let's add electron pair down there. That means that our our base is gonna be an electron pair donor, and our acid, if it's a proton donor, is gonna be an electron pair acceptor. So you can see what I'm trying to do in here. So then, for example, if you already know that your base for Bronsted is a proton acceptor, you can already figure out that for Lewis, your base is gonna be an electron pair donor. So then if you already know the definition, which is nice because since if you know the definition of another one, you can kind of build this charge, and then you would already assume, or you would already know the definition for each one. So throughout the rest of these slides, I would really recommend to do like a little chart and then really use it, and it's really gonna help you out with Bronsted-Lowry base and acids. Okay, so conjugate bases. So draw the conjugate base for each of the following compounds. So then conjugate acid and conjugate base. So my trick for this ones is that when I do a conjugate base, like I would say, A, B, C. So then A is always the first place, and base is always the second place. This is just my logic, just so I can remember how to do these problems. So then I would think B is second place. So I would think, what's left? What's left is the last place, and then A will be like it will be kind of like the winner per se. So then base, what's left? Winner has more things. So then, let's see. It's gonna make sense later on. So then we're gonna draw the conjugate base for each of the following structures. So then when we're doing a conjugate base normally, we're just gonna remove one proton from the molecule. So that's why I mean when saying what's left, because I'm removing a proton from it. So then when I'm drawing the conjugate base for A, for example, I'm just gonna be breaking this bond that it has with the hydrogen. I'm just breaking it down there. So my conjugate base for A is gonna look like this. That's what I meant with what's left, because I'm removing stuff from it. So then I'm removing a proton from that acid. The same logic goes for B. I'm breaking the bond between nitrogen and hydrogen. I'm breaking the bond and putting it on the nitrogen. So then what's left? We have this down here. And then NH4 plus. So then conjugate base, what's left of it, we're gonna remove one proton from it. Just gonna be breaking this, we're gonna place it on that nitrogen, we have one lone pair. And it's not gonna have any formal charges, just because our nitrogen it's gonna have 3 bonds and it's gonna have a lone pair. It's just nitrogen in its regular state. So I would say I'll just use this knowledge, like conjugate base. Draw the conjugate base for this. So what's left for it? And then that's why I said we did conjugate base, so we're doing conjugate acid. So then let's use the same knowledge. Conjugate acid, it's a winner. It has more things. Well, conjugate base is what's left. So then, if for conjugate base, what's left? We're removing stuff. So then, for conjugate acid, we're adding stuff to it. So then, we're gonna add another hydrogen in it. So then, we can look at this. So then, our carbon, it has a negative, right? Carbon with a negative, it has 1, 2, 3 bonds, and it has a lone pair, right? And these ones in here, they can't really interact at all, just because they already has, it's already in its regular state. They have, for example, this one has 4 bonds, this one has 4 bonds, it has 4 bonds. So the only one that can really interact and get a proton from it is this one down here. So then we're just gonna grab a proton and we're gonna protonate it. So then our conjugate acid for that molecule, it would just be this. So then the logic is like, we're just adding a proton. It's our winner. We're just gonna add a proton. So then just think, A, first place, it has more things. So then more things, in this case, is gonna be 1 more proton. And then base, what's left, is gonna have 1 less proton. So then let's look at B. So then B, we have, CH, H, CH, H, and then have CH, H, H. And then this one has a lone pair. It's the only one that can really get a hydrogen from it. So then we're gonna use the lone pair, and then we're gonna grab a hydrogen. So we have 1, 2, 3, nitrogen, 1, 2, and then hydrogen with another one. And then it's gonna have a positive charge, because nitrogen with 4 bonds, no lone pairs, it's gonna have a positive charge. So then NaOH. So then things that Na, they're just as spectators. So technically they're not there. So then every time you see something like Na, you can think about it like it's not there. So then it's just gonna be an oxygen with a negative charge, just bonded to 1 hydrogen. So then we're gonna do its conjugate acid. We're just gonna add a proton to it. Then that oxygen lone pair is gonna grab that hydrogen. And oxygen is in its regular state. It has 2 bonds, 2 lone pairs, so there's no need of formal charges. So hopefully my little logic on acid or conjugate acid been a winner, and it has more things. It has 1 more proton, and conjugate base, it's what's left, and it has 1 less proton. It kind of helps you out when you do this type of problems. Okay, so identifying bases and acids. Identify the lowest acid and the lowest base, and identify the Bronsted base and acid. So like I said, when I do this on test, I would really like you guys to do a chart possibly. So you have acid, and it's pretty quickly if you think about it. It doesn't take a lot of time. Acid, base, we have Bronsted, and then we have Lewis. So you have our Bronsted acid, what we said, Bronsted acid, Bronsted base, Lewis acid, Lewis base. And I know the definition for Bronsted base. So Bronsted base is gonna be a proton acceptor. So this one's gonna be a donor. And Bronsted have to do with protons. Proton donor. Then our Lewis, it has to do with electron pair. So we have electron pair. Let's see, this one's donor, so this one's gonna be acceptor. And we have electron pair acceptor, this one's gonna be a donor then. And then just let me check back on my chart, I don't want to get it wrong. So then we did proton acceptor, Bronsted. Proton acceptor, Bronsted. Okay, so we're good to go. So then we're doing identify the Lewis acid and the Lewis base. So then I would say first just add your electron pairs. So then let's look at our chart. Our acid is going to be an electron pair acceptor, and our base is going to be an electron pair donor. So then our oxygen is actually, if it's going to attack on here, down here. And if you think about it, we know that our base is going to be an electron pair donor. The oxygen is donating an electron pair to that boron. So then we can say that this one is our base. And we can say this one is our acid. And then we're going to do the Bronsted-Lowry base and acid. So then let's add our electron pairs. And then oxygen without positive, it only has one lone pair. Okay, so then nicely we are already given the products for this one. So we can see that we're gonna take one oxygen. So then we're gonna start our tail from our arrow on that on that electron pair from that oxygen, and we're gonna place the head of the arrow on a hydrogen. And since hydrogen can only do one bond, we're gonna break that other bond that it has with that oxygen, and we're gonna place it on the oxygen. So then let's see, and then this one has only one. Okay, perfect. So then Bronsted-Lowry, so then our Bronsted-Lowry base and acid. Okay, so our Bronsted base is gonna be a proton acceptor. So then this molecule, if you think about it, is accepting a proton. It's taking a proton from the other molecule. So that's what makes it a base. And then the other one, it has to be an acid. Since it's the proton donor, the base is taking a proton from that acid. So then if we have our base, on the other side, it's going to be a conjugate acid. And we have an acid, on the other side it's going to be a conjugate base. And see, if you know the definitions, it's actually pretty much easier. It's much easier to know which one's the lowest acid, lowest base, or Bronsted base and acid. Okay, so we're gonna look at aerial. I really like aerial. I think it's really easy, and after you get the hang of it, I think you're gonna really enjoy it. So then aerial, it stands for atom, resonance, induction, and orbital. So atom, where's the negative charge located? So then we're gonna compare electronegative. If we have one that has a negative charge on a nitrogen and one has a negative charge on an oxygen, well, the most acidic one is gonna be the one that has a negative charge on that oxygen. So then, for example, in here, let's see a carbon negative and an oxygen negative. Well, the oxygen is going to be more acidic than that carbon. But if we have an oxygen negative and a sulfur negative, like you see, they're on the same column, the sulfur is going to be more acidic. And you're going to wonder why. Because when they're on the same column, what matters is the weight, not how electronegative it is. So this is on weight. But instead, when they're on the same row, what matters is electronegativity. Okay, so resonance. Resonance is kind of like, if your molecule has resonance, it's going to be more acidic. Induction. So then in here, we know that our pKa values go from negative 10 to 50. Negative 10 is most acidic, while 50 is going to be less acidic. So then we already know that it's going to go from this. It's going to be most acidic. So then induction, it means that there's like an electronegative atom like chlorine, bromine, iodine, that is just gonna pull away the charge from it, which makes it more stable, which makes it more acidic. So then you can see here, this one, it doesn't have any induction, so it's less acidic. Well, we're adding one induction factor in here, and it makes it more acidic. We add 2, and it's way more acidic than one that only has 1. And this one that has 3 is way more acidic than the other ones before it. So the more induction factors you have, the most acidic your molecule is going to be. And then orbitals. So we learned to read orbitals, right? So then we have 1, 2, 3, 4. This one's going to be sp3. We have 1, 2, 3. This is going to be sp2. And then we have 1, 2. This is going to be an sp. So then technically, when we're dealing with orbitals, an sp is going to be more acidic than an sp2. So we're going to draw another arrow. It's going to be making most acidic. So sp, more acidic. Okay, perfect. And then this is the last one I would say for you guys to know. So then you can see that the tert-butanol is way less acidic than ethanol. The main difference is that ethanol is less bulky than tert-butanol. So that's what makes it more acidic. So then when it's less bulky, it's going to be more acidic than one that's really bulky. So we look at how bulky it is. So I would say that you need to know those factors when you're doing aryl or when you're comparing acidity. Okay, a strong to weak acid. Rank the following compounds from strongest to weakest acid. Okay, let's see. Okay, so then when we're doing acidity, we have to draw first the conjugate base for each one. Conjugate base, remember, it's what's left. So then we have to draw the compound without all of the compounds without a hydrogen atom. So let's do that. So then we have this, oxygen, chlorine. You have 1, 2, 3, 4, oxygen, negative charge. We have 1, 2, and then we have bromine. Then we have bromine with a negative. It's gonna have 1, 2, 3, 4, 5, 6, 7, 8. And then we have chlorine with a negative. It's gonna have 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. So now let's look at aryl. Okay, so we can look at atom. Let's look at atom. Okay, nice. Okay, so then our negative charge is placed on the first molecule. Our negative charge is placed on an oxygen. Second molecule, our negative charge is placed on an oxygen. The third molecule, our negative charge is going to be placed on a bromine. On the last molecule, our negative charge is going to be placed on a chlorine. Okay, perfect. So then we have A. We can do R, and R. So then we have resonance. There is resonance for this one, so this one has resonance. This one has no resonance. I, there's induction. Why do I say there's induction for this one? Because there's gonna be a bromine and a chlorine. And then while the other ones, they don't have any induction. And then let's see, when we do orbitals, this one's just gonna be sp3, this one's just gonna be sp3, this one's just gonna be sp3 as well, this one's just gonna be sp3 as well. So technically orbital's not really gonna affect that technically. Okay, so now we have all of our factors. So area is gonna be, it's called area because that's the order of, like, for example, the atom, for example, if we have to look at atom or resonance, if our atom is placed, like, if our negative charge is placed on nitrogen, we're comparing, for example, nitrogen and a carbon negative, and then they both have resonance, but the negative charge is placed on a nitrogen atom, so then still this one's gonna be more acidic. So then let's see. So then we already know, if we look at our little periodic table down here, or in this one down here, so then we can see that we have an oxygen, but then we can see that chlorine and bromine, they're more electronegative than oxygen. So then number 3 and 4, they're gonna be more acidic than 1 and 2. So then we have bromine and chlorine, right? So then what we said, when they're on the same column, what matters is the weight. So then bromine is gonna be more acidic than chlorine. So then this one is gonna be our first place. This is gonna be our second place. So now we have to find out between the first molecule and the second molecule. We have to find out which one's more acidic. So then they both have an oxygen with a negative, so we can eliminate that. They both have the same resonance, we can eliminate that. They both have the same orbitals, we can eliminate that. They both have the same induction, but not really. So then when we're talking about induction, chlorine is more electronegative than bromine. So that means that chlorine is pulling away those charges more strongly. So that means that makes our compound more stable, which means that this one is gonna be more acidic than number 2. So then this one is more electronegative, which makes it more stable. So hopefully this was pretty helpful for you. If not, you're always welcome to come to my office hours if you have any more questions about identifying which one's the strongest or weakest acid. And then let's see, we're gonna determine which product is more acidic. So for this, in these problems, they're just trying to tell you to draw the compound 2 different times and remove the product. So then, for example, in here we're still gonna have our H, but this one's gonna be the negative. On this one, it's gonna be the negative H, the negative carbon. So then, if we look at those 2, we have our negative charge on a carbon, right? So then our main factor, I would say, is resonance. So the thing is that this one, it can do resonance, while this one can't do resonance. Why can't do resonance? Because the carbon is already placed on a double bond, which makes it localized. So that means that this carbon cannot do resonance. So then that means that this one is going to be more acidic. Okay, perfect. So then let's look at the next one. We have nitrogen, hydrogen, We're gonna draw two molecules, and then we're gonna remove a proton from each one. And I'm really sorry if they don't look that pretty. Let's see. Let me erase this. I did it wrong. Have this. And let's see. 1, 2, H. Okay. 1, 2, 3, H. Okay, let's see. This one has 1, 2, 1, 2. This one has a negative. Okay, perfect. So if we look at the two molecules, they both have a negative charge on the nitrogen. So technically, atom is not really going to help us. So then we can move to resonance. So then by looking at resonance, if we look at the number of carbons we have, this carbon, for example, it has three hydrogens. So technically, it's not going to participate in resonance. So then if that carbon doesn't participate in resonance, that means that this nitrogen is not going to be able to participate in resonance. So it's just going to be stuck in there. Well, this nitrogen, it is going to participate in resonance. And resonance is one of our factors to knowing which is more acidic. So since this one can actually participate in resonance, this one's going to be more acidic than the other one that can participate in resonance. And I think the last one's pretty easy, since we already know that if we're comparing an oxygen negative and a sulfur negative, our sulfur is going to be more acidic, right? Because it weighs more. So then this one's going to be more acidic. Okay, perfect. So some things that we have to consider. Our pKa values come from -10 to 50. -10 is going to be the strongest acid. 50 is going to be our weakest acid. And equilibrium always favors the weakest side. And arrows begin at a lone pair. And of course, they're going to always begin at a double bond or a triple bond when doing resonance. Okay, so we're going to determine the equilibrium with pKa values. Let's see. So then we said that pKa goes from -10 to 50. -10 being the -10 being the strong acid, and then 50 being the weak acid. So then let's see. We have to identify which ones are base and acid first. Okay, perfect. So then let's see. This electron pair is going to take a proton. We're going to be breaking that bond with that oxygen. So we're going to place our tail on that single bond and put it on that oxygen. Arrows normally go from base to acid. So we already know this one's going to be our base. This one's our acid. Let's see. This one's going to be our conjugate acid. And then this one's going to be our conjugate base. Let's see. If we're looking at our acids, for example, the one that has the -7.3 is going to be stronger than the one that has -1.74. So this one is our strong acid. And in reverse, on the other side, is going to be a weak base. So then something that is a strong acid, on the other side is going to be a weak base. The same knowledge goes for this one. So then we have a weak acid. On the other side, it's gonna be a strong base. And we have to remember equilibrium favors the weaker side. So then our equilibrium is gonna go that way. This way. So this is for us to determine the position of equilibrium with pKa values. But what if we don't have any pKa values? That's a little bit much harder. So for those ones, we normally use Aereo as well, which is pretty helpful to determine which one's more acidic than the other one. So first, we're going to start to determine which one's our base and which one is our acid. So then let's see, we're going to look at reactants from products first. So then that nitrogen is taking a hydrogen from it. Oops. So then we already know this one's our base. This one's gonna be an acid. This one is our conjugate. This is our conjugate base. And this one's our conjugate acid. Normally, when we're comparing pKa values without, let's say, without, when we're comparing acidity without pKa values, we look at the base. So we're gonna compare these two, okay? And then we can use Aereo for that one. So then we have we have our nitrogen negative. Okay, so we have no induction. Our orbitals are the same for each one because it's going to be placed on a negative nitrogen. So then resonance. So then they both have the same resonance if you think about it. It's going to go from here to here and here to here. The main difference is that oxygen is more electronegative, so that means that it's going to stabilize that negative charge way better than a sulfur. So then this one, I would say stabilize better. So that's going to mean that this molecule down here is gonna be your strong acid, and this one's gonna be your weak base. So then when we do Aereo and we're comparing molecules, we're comparing acidity, yes. So then the winner for Aereo is gonna be the strong acid weak base. So then we said it's gonna be a strong acid, so that's why on the other side is strong acid, but in this side it's gonna be a weak base. And same logic was for the other one. The other one was a weak acid, right? So then on this side it's going to be a strong base. And equilibrium favors the weak side. So then it's going to favor this side over this one. So there you go. That should be everything that you have to know for this exam one. But of course, if something wasn't really clear enough for you guys, you're always welcome to stop by anytime during my office hours, and you can totally write an email to me and I'll try to answer you as soon as possible. So good luck for this exam. I really think you guys got this, and I hope you have a wonderful weekend.